All right, let's jump right in. We take something like 20,000 breaths every single day, and we barely think about any of them. It feels so simple, doesn't it? Air in, air out. But underneath that easy rhythm, there is an absolutely incredible, complex machine at work. So today, we're going to pull back the curtain and follow the journey of just one single breath.
So let's start with that big question. What's actually happening when you take a breath? I can tell you, it's so much more than just filling your lungs with air. It's really this amazing two-part story that connects the air all around us to the deepest, most critical processes happening inside every single cell in your body.
Okay, so first up, you've got what's called external respiration. This is what we all picture, right? Air moves into the lungs, oxygen jumps over into the blood, and carbon dioxide comes out. Simple. But, and this is the really cool part, there's a second act. It's called internal respiration. This is where things get personal, right down to the cellular level. Your blood plays delivery driver, dropping off all that oxygen to your cells. And then the tiny powerhouses inside them, the mitochondria, use it to create the energy that literally keeps you alive. They're like these tiny little engines in every one of your cells.
Now, to get all that work done, your body has this amazing engine room. It's this perfectly coordinated dance of muscles and pressure changes that drives the whole process. So, what do you say we pop the hood and see exactly how this engine works? Let's start with just one single breath in.
So breathing in, that's called inspiration, is actually an active job. Your body has to do something. First, a couple of key muscles get to work. Your diaphragm, this big muscle at the base of your lungs, it pulls down. At the same time, the muscles between your ribs pull your whole rib cage up and out. All of that makes your chest bigger, creating more room inside. And that extra space means the pressure inside your lungs suddenly drops. It's now lower than the air pressure outside. And you know what happens then? Physics takes over. Air rushes in to fill that low-pressure zone, just like a vacuum.
Okay, but here's what's kind of mind-blowing. A normal, relaxed breath out, it's completely passive. Your body doesn't have to do a thing. Those muscles that were just working so hard, they just relax. The diaphragm pops back up, the rib cage settles back down, and the whole chest area gets smaller. This gives your lungs a gentle squeeze, the pressure inside goes up, and the air just flows out. No work involved. It's pretty amazing.
All right, so we get how the air moves. But how much air are we talking about here? Well, doctors have a whole system for this, kind of like keeping a ledger for your lungs. It's how they figure out how healthy they are. And these measurements are called lung volumes and capacities.
Let's start with the most basic one, tidal volume. Just think about the breath you're taking right now as you're listening. That normal, quiet, you're not even thinking about a breath. That's it. That's your tidal volume.
So how much is that? Well, on average, it's about 500 cubic centimeters. Now, to give you a better picture, that's roughly the size of a regular water bottle. Yeah, really. So with every single calm breath you take, you're moving a water bottle's worth of air. And you're doing that, what, 12 to 16 times every single minute? Wow.
But obviously, we can breathe in way more than that, right? That huge, deep breath you can take after a normal one, that extra bit has a name, the inspiratory reserve volume. And get this, it's enormous. We're talking about 3,000 cc. That's your about to dive underwater or your I really need to calm down breath.
And it works the other way too. After you breathe out normally, you can still keep pushing more air out, right? That extra amount you can force out, that's your expiratory reserve volume, and it's about 1,100 cc's. Think of it as your birthday candle blowing out power.
So, a question for you. After you've pushed out every last bit of air you possibly can, are your lungs totally empty? The answer is nope, not even close. There's always about 1,200 cc's of air just hanging out in there. This is called the residual volume, and it's absolutely crucial. It acts like a little support structure to keep your tiny air sacs, your alveoli, from just collapsing on themselves.
Okay, so we've got all these individual numbers, these volumes. A good way to think of them is like ingredients in a recipe. When you start adding them together, you get capacities, and capacities tell a much bigger story. For instance, if you add up your normal breath, your big inhale reserve, and your forced exhale reserve, you get your vital capacity. That's all the air you can actively control. And then, if you add that last little bit, the residual volume that's always there, you get your total lung capacity, the absolute max your lungs can hold, the whole shebang.
And the crazy thing is, all of this is happening on autopilot. You're not sitting there thinking, okay, diaphragm, contract, now relax. So who's in charge here? Who's running the show? Well, the answer is deep inside your brain, in the oldest, most fundamental part. It's your body's incredible control center.
This control center is actually a few different groups of neurons tucked away in your brain stem. You know, that's the part that connects your brain to your spinal cord, the part that handles all the stuff you never think about, like your heartbeat. These little clusters in places called the medulla and the pons, they're the ones creating that steady in and out rhythm of your breath. They're the reason you keep breathing even when you're fast asleep.
But this autopilot isn't just mindless. It's incredibly smart. It's constantly getting real-time updates from a whole network of tiny chemical sensors. You've got some right in the brain and others in your big arteries, and they're all doing one thing, 24/7. They're tasting your blood to see what's going on.
So what are they looking for? You'd probably guess low oxygen, right? That seems logical. But here's the twist. The main thing that makes you want to breathe isn't a lack of oxygen. It's a buildup of carbon dioxide. Let that sink in. Your urgent need to take a breath is driven more by the need to get rid of CO2 than the need to get more O2. When that CO2 level starts to climb, it's like a huge alarm bell goes off. The sensors scream at your brainstem, "Hey, we gotta clear this stuff out." And boom, you start breathing faster and deeper. So now that we have all these pieces, the mechanics, the measurements, the brain's control system, let's connect it to the real world. This whole system is a thing of beauty when it's working right. But what happens when it goes wrong? Well, understanding all this is exactly how we can figure that out. Generally speaking, most lung diseases fit into one of two big buckets.
First, you have obstructive diseases. Think of things like asthma. Here, the problem is in the pipes. The airways are blocked or narrowed, so air can get in okay, but it gets trapped. It's hard to breathe out. And doctors can see this with a test that measures how much air you can blast out in 1 second. If that number is low, it's a sign of an obstruction. Then you have restrictive diseases, like pulmonary fibrosis. Here, the pipes are fine, but the lungs themselves are the problem. They're stiff, they can't fully expand, so the main issue is not being able to breathe in enough air. And that shows up as a low vital capacity. The total amount of air you can move is just smaller.
So if you're going to remember just one thing from this section, let it be this simple phrase. For obstructive disease, the problem is you can't get the air out. For restrictive disease, the problem is you can't get the air in. That's really the core difference, boiled down.
It's pretty incredible when you think about it. Breathing isn't just one thing. It's this perfect symphony, right? You've got physics moving air around with pressure, chemistry with all those little sensors tasting your blood, and biology with the muscles and nerves making it all happen. It's this powerful, yet incredibly fine-tuned system, working perfectly with every single breath.
And that brings us to a final little thought experiment for you. We just found out that the big red button for Breathe Now is rising CO2. So what do you think happens if you try to trick the system? What if you hyperventilate? Breathe really fast and deep for a minute before you try to hold your breath. What is that doing to your CO2 levels, and how would that affect your body's automatic response? It's a pretty cool way to see the connection between something you choose to do and that ancient, powerful autopilot running the show in the background.